Section 8.3 is on rational functions and their graphs. A rational function is a function in the form of f of x equals p of x over q of x, where p of x and q of x are polynomial functions. So for example, f of x equals x squared plus x minus 12 over x squared minus 4 is a rational function because we have a polynomial in the numerator and a polynomial in the denominator. When we want to graph a rational function, it's helpful to first identify some key parts of the graph, and those are horizontal, vertical, and oblique, sometimes called slant asymptotes. So where are my asymptotes, and draw those in. Any points of discontinuity, any breaks in the graph, is there a hole somewhere where x can't be a certain value, and to identify the x and y intercepts. Now, here are some hints on how to do those things. To find a horizontal asymptote, we want to compare the degree of the numerator, which we're going to call m, to the degree of the denominator, which we're going to call n. If m is less than n, if the degree of the numerator is less than the degree of the denominator, then the graph has a horizontal asymptote at the line y equals 0, in other words, the x-axis. If m is greater than n, that is, the degree of the numerator is greater than the degree of the denominator, the graph has no horizontal asymptote. And if m is equal to n, then the graph has a horizontal asymptote at the line y equals a over b, where a and b are the leading coefficients of the numerator and the denominator, respectively. In other words, your horizontal asymptote is going to be the leading coefficient of the numerator over the leading coefficient of the denominator. A vertical asymptote occurs at q of x equals 0 if p of x and q of x have no common zeros. In other words, a vertical asymptote is going to be the value of x that makes the denominator 0. That is, if they have no common zeros, that'll cancel out. We'll take a look at that. An oblique or a slant asymptote occurs when the degree of the numerator is 1 more than the degree of the denominator. So in other words, if I do the degree of the numerator minus the degree of the denominator, if that equals 1, then I know that I have a slant or a not vertical or horizontal asymptote. And the equation of that line is p of x divided by q of x with no remainder. A point of discontinuity, or a hole in the graph, occurs when q of x, the denominator, is a factor of the numerator. We'll take a look at an example of that. X-intercepts occur when p of x equals 0, in other words, when the numerator equals 0, and y-intercepts occur when x equals 0. So let's take a look at a couple examples here. And because this takes a long time to do, I've gone ahead and done some of the work in advance here. There we go. Okay, so here we have, let me get a little bit more there. Graph each rational function. We need to identify the asymptotes, the intercepts, and if there are any points of discontinuity, and then state the domain. Number 1 is f of x equals 3 over x squared minus 4. A really useful thing to do is if you can factor any of these polynomials, do that first. X squared minus 4 factors into x plus 2, x minus 2. Therefore, because that's in the denominator, that means that I'm going to have a vertical asymptote when each of those equals 0. So I'm going to have a vertical asymptote at the line x equals 2, and that's this line right here, I drew in red, and a vertical asymptote at the line x equals negative 2. Those are the easiest ones to find first. I'm going to have a horizontal asymptote at the line y equals 0, or the x-axis, because the degree of the numerator is less than the degree of the denominator. The degree of the numerator is 0, degree of the denominator is 2. Now let's find our intercepts. So when x equals 0, when I plug in 0 for x, I get that y equals negative 3/4. Therefore, my y-intercept is going to be negative 3/4. And f of x cannot equal 0. In other words, my numerator can never equal 0, so I'm not going to have any x-intercept. So let's go ahead and graph those points. Well, I put the vertical and horizontal asymptotes in there already. Let's go ahead and graph the y-intercept, which is going to be kind of down here. Now that doesn't tell me a whole lot about what the graph looks like. So let's go ahead and choose some points that are near the vertical asymptotes. In other words, a few points on either side. So I got negative 3. So when I have the point negative 3, I have 0.6, which is a little more than half. Whoops. And when I have negative 4, it's like 1/4. So it's actually, whoops, that one disappeared, kind of down there. So this part of the graph I can presume is going to go something like that, since it's going to work around my asymptotes. Okay, same thing on the other side. I actually have some symmetry in this graph. So at positive 3, I'm going to have 0.6, whoops, that disappeared. And then at positive 4, I'm going to have 0.25. So again, I don't know why my dots are disappearing there. I'm going to have a graph that should be a little more curved there. It should look something like that. Okay, and then looking at what's going on in the middle here, I chose the point -1 and I got -1, and I chose +1 and I got -1. So this part of the graph is actually going to go like this. And next I need to figure out what my domain is, and my domain is what values x can be. X can be all real numbers except for +2 and -2, because those are the values that are going to make the denominator 0. Let's take a look at another example here. Here I have f of x equals x squared minus 3x minus 4 over x minus 4. Notice that the numerator can be factored into x plus 1 x minus 4, and then actually what's going to happen is these are going to cancel each other out. The numerator and the denominator have common factors. So my graph is really going to be f of x equals x plus 1, or the line y equals x plus 1, but I'm going to have a point discontinuity. I'm going to have a hole at x equals 4 because that's the value that would make my denominator 0. Okay, let's go ahead and graph that. It's easy to graph the line y equals x plus 1. So I would have my y-intercept of 1, and I have a slope of 1 going up like this, but when I get to 4, when x equals 4, I'm going to have a hole in the graph. Okay, and then I have a few points going this way. So this graph is going to look like this. It's going to be basically the line y equals x plus 1, but with a hole at x equals 4. My y-intercept, I can get that from the equation here, is 1, and my x-intercept is a -1, and my domain is all real numbers except for x equals 4. Let's take a look at a third example here. Wait for some of the notes to come up here. Okay, so here we have f of x equals x squared minus 1 over x squared plus 3. I went ahead and I factored my numerator. X squared minus 1 is an x plus 1, x minus 1. And looking at my denominator, I'm not going to have any vertical asymptotes, because when I set the denominator equal to 0, x squared plus 3 equals 0, and solve that for x, I get that x is the square root of -3. It's not a real number, so I'm not going to have any vertical asymptotes in this graph. I'm going to have a horizontal asymptote at y equals 1 because the degree of the numerator is equal to the degree of the denominator. It's x squared over x squared. So remember, that means that I'm going to have a horizontal asymptote at the equation y equals whatever the leading coefficient of the numerator is over the leading coefficient of the denominator. So the leading coefficient of the numerator is 1, as is the leading coefficient of the denominator. So the line is y equals 1 over 1, or a horizontal asymptote at y equals 1. Let's find our intercepts. So when x equals 0, y is equal to -1/3, so I'm going to have a y-intercept at -1/3. And my whole function equals 0, or y equals 0, f of x equals 0, when my numerator equals 0. X squared minus 1 equals 0, so that means my x-intercepts are going to be 1 and -1. So let's go ahead and graph those points. So my y-intercept is -1/3, so something right about like there maybe. And then my x-intercepts at +1 and -1. And I'd kind of like to know what's going on. Clearly I can almost have like a V shape here, but I know it can't go above my horizontal asymptote of y equals 1. So if I look at a couple other points, -2 and +2, I get almost like 1/2, so something like this. So my graph is going to look something like this. And it's going to approach that horizontal asymptote but not cross it. And in this case, looking at the graph, basically because there's no vertical asymptotes or holes in the graph, my domain can be all real numbers. I have no restriction on my values of x's. Let's take a look at our last example here. F of x equals x squared minus x over x plus 1. And I went ahead and I factored my numerator. All I can do is take out a greatest common factor of x. And vertical asymptote is going to be the value of x that makes my denominator 0, so that's going to be at x equals -1. And I have no horizontal asymptote because the degree of the numerator is greater than the degree of the denominator. That's 2 over 1, so no horizontal asymptote. However, I am going to have a slant asymptote because the degree of the numerator minus the degree of the denominator equals 1. Degree of the numerator is 2, degree of the denominator is 1, 2 minus 1 is 1. So I have to do a little division. I basically have to do x squared minus x divided by x plus 1. And if you recall from a couple chapters ago, we can do this since the leading coefficient of my denominator is 1. I can go ahead and do this using synthetic division. So remember, put the -1 in the box, list the coefficients from the top, so that it'd be 1, -1, and 0. Bring down the 1. -1 times 1 is -1. Add gives me a -2. -1 times -2 is 2. Add, that gives me 2. So this means that this is the equation y equals x minus 2 with a remainder of 2, but we don't worry about the remainder when we're looking for a slant asymptote. So I'm going to have a slant asymptote at the line y equals x minus 2, which is this red line that I've done right here. So let's take a look at a couple values for our intercepts. When x equals 0, y equals 0, because I'm going to end up with a 0 on top. That's going to give me the origin basically is going to be one of my points, 0, 0. And f of x equals 0 when my numerator equals 0, so x equals 0, we already had that one, or x minus 1 equals 0, so I have an x-intercept at 1. So that's going to be this point right here. And I went ahead and plotted some, or looked up some additional points here. So when x is, I'd kind of like to know what's going on in here. So when x is 1/2, y is -1/6, which I can't really graph, so that's going to give me something that looks like this. This is going to curve and go up like that. And then I wanted some points over here. There's going to be something going on over here. So when x is -2, y is -6, which is going to be right there. When x is -3, y is -6. And I'm going to presume that it's going to kind of do the same thing with my asymptotes here. Okay, that's not real smooth, but you get the idea there. Okay. Oh, and then my domain is, I think I wrote my domain down here. Here we go. X is not equal to -1 because that's the value that would make the denominator 0. So in this section, I apologize, it was kind of a long video. We took a look at rational functions and their graphs, basically how to graph them and some of the rules. Please do refer to that first page of notes that I went over, which tells you how to find your asymptotes, how to find your points of discontinuity, and x-intercepts.